carbon nanotubes, so possibly a linked presentation topic there. And I'd like to introduce him to you as we get him on board. He leads the effort to develop and commercialize carbon nanotube-based performance additives for cement, concrete, and lithium-ion batteries as well. He has more than 35 years of senior techno-commercial leadership globally, including being CEO of QM Power, an electric motor startup in Kansas City in Missouri. He's been VP of Innovation, Sustainability, and Technology for Ingersoll Rand Train in Charlotte, North Carolina, and he was the president and CTO of the USHA, which is a leading consumer brand in India. Harry, can you hear us?
Yes, I can, yeah.
Great, we can hear you too. If you wouldn't mind just putting your PowerPoint into presentation mode, slideshow mode, that would be great. So Hari Kumar holds a master's degree and a PhD in aerospace engineering from the Indian Institute of Science in Bangalore, as well as a Bachelor of Science degree in mechanical engineering from the NIT Calicut in India. There we go. Okay, so Hari, we can now see you and hear you, and your PowerPoint is in exactly the right format. So please do go ahead and give us your presentation. Thank you very much.
Okay, great. Thanks a lot. Hey, thanks a lot for arranging this program, and it was really a pleasure to also listen to the previous presenters. I think Jared and Ray on what they're doing with graphene. And so we as a company, CHASM, have been working on carbon nanotubes for various applications. And here is our venture into concrete over the last 2 years, I guess. And we've been making a lot of progress, and it'll be my honor to share our progress. And as previous presenters shared, we need more collaboration, and kind of combined we can bridge the gaps. So CHASM as a company has been into nanotubes for a little over 15 years. Have been into various applications, and the products we have already got in the market are on the right hand side, which are more performance films, which are transparent heaters and transparent antenna. Transparent heaters have picked a lot of attention, especially with the ADAS, kind of all the automotive driver assist systems on a car. And then I joined the company a few years ago when we started to see an opportunity on the additive side of the nanotube business. And a lot of people have tried applying nanotubes and nanomaterials in general as a volumetric additive, but there have been a lot of barriers. And we are into two areas, batteries and concrete. Batteries, the application space has really progressed, and we are more catering to it than developing it, but really accelerating it. And concrete, we have to develop and cater to it, and that's the journey which we are in. So in short, why concrete? So it's been long known. In fact, concrete was almost one of the first applications nanotube was tried on. It was known that if you disperse it well, you get very good early strength. And these are mortar level tests reported by our university partner. You get long-term strength, you get high stiffness on mortar, and flexural strength literally doubling. And this was amazing. But however, this could not be translated directly to the industry. Why? One is cost, as some of my earlier colleagues spoke as well. Cost is critical, dispersion is critical, and scale is critical. And to cater to all these three, nanotubes are, and some of you might wonder what are nanotubes. My previous presenter spoke about graphene. If you fold them into a cylinder form, like a cylinder, it's a tube that's called a single wall nanotube. If you have a Russian doll-like model with multiple tubes, that's a multi-wall nanotube, as you see on the extreme right. The diameters we are talking about in concrete are around 10 to 15 nanometers in diameter, and length as made maybe around 5 to 10 microns, but as you disperse, it would be much shorter. So how do you make nanotubes? Nanotubes are conventionally made in what are called fluidized bed reactors, which are pretty expensive and capital intensive. And so our approach was, how do we pivot to a scalable process? So we went to a rotary kiln reactor, so which is like a mini cement plant. So what you see on the right is ethylene coming in, and all the carbon from the ethylene is sequestered into the nanotube. Sounds very simple, but there's a lot of complication behind it. Our CTO has got certain proprietary mixes on the catalyst powder, which makes it possible to use a rotary kiln to make nanotubes? And then the next challenge, and of course, when you make in large scale, we put ourselves a target. Cement today is at a marginal cost of $50 a ton as made by the cement manufacturer and sold in the market at $100 to $150 a ton. And so unless you are in the ballpark at a ton level, which is in tens and $20 of additive to be added to a ton of binding material, you really cannot make sense. And so we use this to get into that ballpark. And then came the problem of dispersion. And dispersion, universities have been using liquid as a form of an intermediate dispersion, and we realized this is not going to work. So we kind of pivoted into two forms of dispersion. One is like a solid dispersion where you directly deposit the nanotube on the cement, and this is what we are kind of going further with. And the second one, which we're also working on, is a microencapsulated granule where you encapsulate it in water-soluble systems. And these two forms of dispersions has made it possible for us to cross the dispersion barrier. And as we prepare for the scale, we are also preparing the world's largest CNT reactor. We are currently at a 50-ton. We're taking it to a 1,500-ton reactor, which is being built in Norman, Oklahoma at our facility. And we intend to build a lot of these as we cater to the battery market as well as the cement market, as the manufacturing platform is indeed common. Now, how does it look like if I take the case of directly depositing on cement, how does it look like at a microscopic level? At a microscopic level, what you see is clusters of nanotubes attached to cement, and you'll never find a free nanotube, because good thing about nanotube is they want to stick to things. Good and bad thing is they want to stick to each other, but as long as you can fibrillate them and make them stick to cement, they'll stick to cement forever. It's in fact impossible to get them apart. So what this does is you have now a specific surface area, say, of cement, roughly around 100 to 200 meters square per kg, supplemented by something which has a similar SSA or specific surface area, except it is meters square per gram, 100 to 200 meters square per gram. And suddenly you're creating a surface area which is like much, much higher, even with dosages as low as 0.15 or 0.1%. And so we took that composition of 0.15 to 0.2% and went back to our university partner with three kinds of cement, one from the US, one from Europe, one from the Middle East, just to get some global mix into the game, and went through the regular ASTM test. And what came out was very interesting. So if you look at what you have here on the flexural strength, with this being the baseline, you would see almost across the board, the flexural strength, moved up to, 70 to 80%. Of course, in my previous chart, I showed 100% increase with the liquid dispersion. The solid dispersion, that takes a beating, but still you are at a 70% level, which is considerable. And this is across various grades of cement from across the globe. And we'll come back to flexural, and it's as high as 75%. And now when you go to stiffness, it goes up to considerably, but though I'm not too sure how much of this will translate to concrete, but it's just a point to be noted. And now we come to compressive strength. You get early compressive strength, at least on two of the three grades, which are of the order of 35% on a 3-day level. At the 2-day level will still be higher gain of the early compressive strength, and a late 28-day strength of around 15%. So we have a bunch of data. These are some eye charts, but I just want to put it out to show that we are not just claiming, but these are deep data behind it, and there's a capture of over hundreds of tests done in the background. So what does it mean? I mean, why does this matter? So what do we do with it? So we kind of went to very similar to our previous speaker's approach. Okay, how do we increase efficiency of concrete? Higher flexural strength can mean thinner pavements or thinner slabs within the compliance of the codes with no change to the cement. So which means it's not all about reducing the clinker, it's about reducing the amount of concrete you use for a particular purpose and yet be code compliant. The second element is to enhance the early compressive strength, which will kind of remove the barrier of some of the SEM adoption which you're seeing. And then there are certain further things which are well studied, be durability of concrete really enhances with very little nanotube due to porosity and porosity reduction, crack resistance, and so on and so forth. And now you have the element of smarter health monitoring, which is a futuristic view, which by the way today is proven in universities where nanotubes display a piezoelectric property, which will allow us to self-sense the stress and state of damages in a concrete at any point of time. So with this, we went down to, okay, how does this now work in the carbon? And by the way, this chart is same as my previous speakers from the GCCA chart. And really what we are focusing on is the top two. So carbon nanotubes uses concrete more efficiently, less clinker in concrete. And improving flexural strength, how much of people might debate, even adding fibers do not improve strength per se. It improves ductility, no doubt. The strength is a little different perspective. And that too, to get a 40-70% increase or a disproportionate increase, nanotube seems to be one of the ways, and I'm open for more collaborations on this. And then clinker reduction, we already spoke about. And if well adopted, this can be, over, almost 0.8 gigatons between the two approaches globally. A deep dive into the thickness on payments. This is from the ACPA tool and a calculation done by one of our friends. And so as you increase the flexural strength, even by moderate 65%, though that's been the minimum we have increased, the thickness can come down by 30% within the code. And this is without including the change of diameters of the, the bars or the dowel pins in the whole assembly. And this would surely reduce CO2 as well. And what does this mean in a little larger perspective? Is on the global, this could mean, tons of CO2 reduction if adopted, not only for payments on highways, but also slabs in building, which further can have a cumulative effect on the overall weight of the structure and foundations and so on and so forth. And on the early strength, this is a graphic borrowed from one of our, partners in the admixture area, where they commonly display if this is a drop in early strength with, say, limestone addition, what an admixture would do to kind of compensate it. And here I just brought in the perspective, my colleagues plotted this plot of drawing the perspective of how does it look when you kind of put the nanotube in, and how can you enhance SCM loading without, having the barrier of reduction of early strength. And hopefully this will increase the adoption. And so what we are trying to present is not a different path, but more a cumulative path with the other approaches. And I'm also open to collaborate with other technologies which are non-steel, like the basalt in the previous presentation, or graphene, and precast in general is surely going to be a trend which we can all play a role. So that's it from my side, and I'm open for questions.
Hi, Harry. Thanks very much indeed. That was a very, very quick canter through the use of carbon nanotubes and your particular kind of carbon nanotube. So thank you very much indeed. And thanks very much indeed for letting us know about what they can do for the performance of concrete. Fascinating stuff. Just like to remind our audience that they can ask any questions via the questions tab. As always, Harry, the question is one of cost, and most particularly cost versus the advantages that these carbon nanotubes bring to the product. So where is the balance? Is the balance in favor of the carbon nanotubes? And is it going to be a case very soon that concrete will be uneconomic without your product?
It's a very good point. And by the way, when I started on this, people were talking of nanotube costs, which are very, very high. And so we had to dig down. Most people were buying purified nanotubes, which with itself doubles the cost. So they say, why purify? And most nanotubes are made on alumina foundation. They say, hey, alumina is friendly with cement. So why do you want to remove it? Keep it. So that removed the purification cost. So alumina was, and then we developed what is called a hybrid concept, where we pre-blend cementitious materials into the synthesis of nanotubes. So that's how we overcame a major step of purification, which we eliminated out of the door. Now coming to synthesis alone, as you saw in my graphic, what comes in is ethylene and a catalyst. And now the cost of cement as made by cement manufacturer is around $50 a ton. The market price of it is around $150 a ton. We are adding 1.15% of nanotubes to it. We have to be in the $10 bracket for the cement guy, in the $20, $25 bracket as dispersed for the market. and those are the brackets which we have hit. So we are into the space which the market can afford. And not only that, with the benefits of thickness reduction and the benefits of enhancing SCM, the net cost is going to be cost positive. What I mean to say is that net system cost is going to be lesser than the cost without the nanotubes. So we are not wanting to have it. So you can have the lower the carbon and lower the cost too, which is why this slogan here is low carbon and low cost. It is not one or the other, but one and the other.
Right. Okay. So I remember from one of your slides, you were suggesting that you were going to dose about 1 kilo of the carbon nanotubes into each 1 ton of concrete. Is that right?
Yeah. So 0.1. So depending on what functionality you want, you can go from even 0.05% all the way to 0.15%. And so that's kind of the range. And if you go too high, you might face into other agglomeration issues and the return may be negative. So one has to be in that range of 0.05. For example, the durability can be kicked in even as low as 0.05. Flexural modulus can come in as low as 0.1. If you want higher flexural strength, higher flexural strength and high early strength, 0.15 is what we have seen with the kind of cement we are playing around with. And as cement chemistry is also fast changing, we'll have to kind of play around with that proportion. Yeah.
Okay, so just to be straight, if you're dosing in at 0.1%, so which is 1 kilo per ton,
Yeah.
From your calculation that you just mentioned, I think that you were suggesting that the cost of this would be somewhere in the region of $15 to $20. Is that right?
Yeah, $15 to $20 a kg of nanotube, which will amount to $15 to $20 of increment to a ton of cement. Yeah.
Yes, that's an amazingly cheap cost.
It is, and and this is possible due to scale. Without scale, it won't happen. The reason we pivoted to rotary kiln, there are only maybe 2 or 3 companies in the world who know to make nanotubes on rotary kiln, but we took that and used our unique catalytic chemistry to scale it up. We also learned from the battery industry as to how to kind of play with dispersions better. So we bought some of the know-hows we learned from battery industry into the cement. We're taking some of the know-how from the cement industry to the battery, by the way. So that's kind of very interesting how we are cross-pollinating the two as well.
Absolutely. So we have a couple of questions that have come in. Tarciso Souza asks, does this process of producing carbon nanotubes on cement today have the capacity to scale? So for example, Harry, you suggested that your new plant would have a capacity of 1,500 tons per year. Is that right?
Yes, yeah. So now the question of, let me clarify. We are not growing it on cement. We are growing it in the vicinity of cementitious material. And once you make the nanotube, we have a method of uniquely depositing it as a post-process, uniquely depositing it on dry cement dust or even SEMs for that matter. So we have a process of depositing it. And reason we could innovate this is because we control the whole synthesis process. We could put some precursors in a way that even at a solid level, they can go where they need to go. We are also developing the admixture kind of route, which is like an encapsulation route, where you would have water-soluble pellets of nanotubes, which will readily disperse. So one solution, we are aiming more for integration into a cement factory or into a grinding facility. Second solution, we are developing more as a drop-in into a ready-mix facility or into a precast facility.
Okay, and just to be clear, both of those dispersion methods would actually bring additional costs to the process, wouldn't they?
Yes, yeah. So, and I've factored those when I spoke about at a cement level what it would cost, and a concrete level, even if you add $5 of dispersion, you're still within the tolerable bracket to still be cost positive. When I say cost positive, I mean lower cost.
Yeah, but largely through using less cement in the concrete.
Yes, either lesser concrete as you make more efficient structure, or lesser cement as you increase SEMs.
Yeah. Okay. And we have another point, I think, from Joanna Roncero. The results presented in the PowerPoint are mortar tests. Do you have concrete tests? Usually mortar demonstrate the differences, and it's important to test things in concrete itself. That's from Joanna.
No, very good question. And we are in this current stage where we want to get our processes right at the motor level, because motor level has less variability and more control by the HTM process. And we have started to get early results on the concrete test, and flexural strength, for example, completely translates from mortar to concrete. In my next presentation, whenever I get a chance through you, I would be presenting the concrete test as well. We have also initiated slab level test and not limited it to the HTM concrete specimen. And same with compressive. Compressive has a little more nuances to it, but we are working on translating most of this to compressive as well.
Very good. Very, very interesting indeed. Harry, do you know what? I think we're going to leave it there. But thank you very much indeed for being with us today. It was a fascinating presentation, and it shows one of the possible pathways into the future. So we really appreciate you being with us.
Hey, thanks a lot, Robert, for arranging this kind of a meeting. Otherwise, I wouldn't know what their thought, other people's thought processes are. And this is a great synergy. And I think the solutions which will emerge is a combination of a lot of these solutions and not a sole one. Thanks a lot.
I think you're right. Absolutely. Thanks a lot, Harry. And we'll see you again another time soon, I hope.
Thank you.
Thanks a lot. Bye for now. Right. Well, that brings us very, very near.